Hi, I'm Devishi Gulati, and the title for my talk is Searching for Triple Grid Diagrams. This is for Nearly Carbon Neutral Geometric Topology Conference 2023. Thank you for inviting me. This is the first part of a two-part talk where I will be focusing on the context and background for triple grid diagrams. Before I talk about the background and motivation, I want to start off by telling you what is a triple grid diagram. A triple grid diagram is a grid diagram on a torus made up of n vertical, horizontal, and diagonal grid lines with dots placed inside such that every row, column, and diagonal contains two dots, differentiated here in this example by x's and o's. Now that we know what a triple grid diagram is, how did they come about? How are they related to grid diagrams, which you might have heard of? And how is any of this related to Legendre submanifolds and contact topology? To begin, I will do a brief recap of what grid diagrams are and their relation to contact topology. Next, I will do a brief overview of what it means for a surface in CP2 to be in bridge position with respect to a trisection. After which, I will talk about shadow diagrams, Legendre tangles, and the motivation for the definition of triple grid diagrams, which represent surfaces in CP2. If you have any questions, please reach out to me. Grid diagrams. A grid diagram consists of an n by n grid with the following restrictions. Each row and each column has exactly one x and one o, and no square can have both. On the left, we have the grid diagram for a trefoil. The x's and o's have been connected by red and blue arcs. On the right, we have the diagram obtained by pushing the horizontal arcs into the screen, away from you, and the vertical arcs out of the screen towards you. In this manner, we can see that the vertical arcs are above the horizontal arcs when it comes to crossings. A grid diagram is a simple combinatorial way to encode a knot in S3. How? It turns out that every knot can be encoded as a grid diagram. Let's see an example which illustrates this process. On the left, we have a projection for the trefoil. The first step is to just take this projection and make it boxy. We get the next diagram. Now, we know for a grid diagram, the vertical lines are above the horizontal. So, at the crossings, we need the vertical to be above the horizontal. In this case, as highlighted by the yellow, we have the horizontal above the vertical. Well, we can adjust this by isotoping it so that now this crossing has vertical above the horizontal. Once we have all the crossings adjusted, all we have to do is put this on a grid square, put points on the corners, and get rid of the arcs. In this manner, I hope to have convinced you that every knot projection gives us a grid diagram. It turns out that not only do we have a grid diagram for every knot, we actually have an equivalence between knots and grid diagrams up to grid moves. Grid moves are translations, commutations, and stabilization. This is even more useful because the Hegat splitting of S3 has the essential surface, which is a torus. And the grid diagrams that we have, we can put them on a torus, as shown in the diagram on the left. Hence, we can encode pointed Hegat diagrams of knots in S3 via grid diagrams, as showcased on the right. This gives us grid homology, which is an invariant for links and knots in S3. How does this relate to contact topology? Well, there is an equivalence between Legendre knots and grid diagrams up to Legendre grid moves, which are a subset of grid moves. How do we obtain a Legendre projection from a grid diagram? So on the left, we have the grid diagram for a trefoil. To obtain the Legendre projection, you turn the diagram 45 degrees to avoid vertical tangencies, smooth the northwest and southeast corners, and cuspify the northeast and the southwest corners, and reverse the crossings. Next, I will talk about the trisection of CP2, what it means for a surface to be in bridge position, shadow diagrams, and how they give us three links in CP2. Here is a schematic of a trisection. CP2 admits a 1-0 trisection. This means that we have three sectors, which are four balls. They intersect pairwise to give us three handle bodies, which are S1 cross P2. And all three of these intersect further to give us a torus. Trisections are 4D analogs of Heggard splittings. Each of these the handle bodies pairwise give us the Heggard splitting of the boundary of B4, which is S3. A trisection is uniquely determined by its spine. Now let's talk about a surface. A surface in bridge position is a surface that has been smoothly isotoped so to sit nicely with respect to trisection. A surface is said to be in bridge position if the intersection with the ambient manifold has the following properties. First, in the sectors, we have a boundary parallel collection of disks, and these intersect to give us a trivial tangle in the handle bodies. Every surface can be smoothly isotoped to lie in bridge position in any trisection of the ambient manifold. Also, a surface in bridge position is determined by its spine, that is, its intersection with the spine of the trisection. So it's really the spine which has all the information that's required, which you can see on the right, where I have three trivial tangles demonstrating this. Shadow diagrams. A trivial tangle means that each arc has a single maximum. Looking at the tangles obtained from a surface in bridge position, we get the corresponding shadow diagrams. These are the shadow diagrams for an unknotted torus. In this section, I will talk about the motivation for defining triple grid diagrams and how the definition came about. Three links. Every link can be represented as a union of two trivial links. So, these pairwise tangles are actually giving us links. For CP2, these links are in the boundary S3 of each B4, as you can see in the schematic. These are the boundary S3 for each B4 sector. If we consider CP2 with the standard symplectic form, the boundary S3 of each B4 inherits a contact structure. And not only does it inherit a contact structure, this contact structure is contactomorphic to the standard contact structure on S3. The tangles obtained from the surface in bridge position can be isotoped to give us Legendrian tangles in the handle bodies. Now, if you look at them pairwise, we're getting Legendrian links in these boundary S3s having the standard contact structure. Can we encode all three of these links in one grid diagram? Now we know we can encode knots in S3 wire grid diagrams, but to encode these three Legendrian links, we need a triple grid diagram. Moreover, we can construct closed embedded Lagrangian surfaces from triple grid diagrams under certain conditions. When all three Legendrian links are unknots with Thurston-Bedicken number -1, we have what is called a fillable triple grid diagram. There's a theorem by Blackwell, Gay, and Lambert-Cole which says a fillable triple grid diagram determines a Lagrangian surface in CP2. With this motivation, we have the definition of a triple grid diagram. A triple grid diagram consists of a grid on the torus consisting of three sets of lines, vertical, horizontal, and diagonal, and 2B points which are in the complement of these lines such that every row, column, and diagonal has exactly 0 or 2 points. A triple grid diagram can be decomposed into three grid diagrams of size B each. Let's look at this example to see how that happens. In the center, we have a triple grid diagram, which is on a torus. It, to get the red-blue grid diagram, all we need to do is forget the green lines, as you can see on the left. Now, to get the blue-green grid diagram, I have repeated this triangle on the right so that we can see the skewed square, the diagonals of which, along with the rows, give us the rows and columns of the green-blue grid diagram. Similarly, repeating the upper triangle at the bottom, you can see how the diagonals, the green diagonals and the red columns give us the rows and columns of the green-red grid diagram. With Now that we have a definition, what are the questions we can ask? Which surfaces are encoded by these grid diagrams? Which Lagrangian surfaces can be encoded by triple grid diagrams? Given a knot or grid diagram, can we make it a part of a triple grid diagram? If not always, when? And when are these two diagrams equivalent? Can we define moves on triple grid diagrams? To answer any of these questions, we need examples. The problem of searching for triplicate diagrams is hard as the diagonal conditions severely limits valid triplicate diagrams. Thank you for listening. I will elaborate on the process and details for searching for triplicate diagrams in part 2 of this talk. I will also talk about the model space of triplicate diagrams and try to answer some of these questions.